Okay, this is now practice exam 2 for your response question number 4. Last one. This one is an interesting one. So we have a unicycle rider accelerates to the right. Unicycle has a single wheel but is otherwise similar to a bicycle. Rider with sufficient practice is able to accelerate while leaning forward to maintain their balance. External forces, so maintain their balance, right away you're thinking that's going to have something to do with torques. Torques are going to balance out, something like that. I mean, I know that's what it is because I've already read the problem, but external forces on the rider unicorn system while balance is maintained and the system accelerates to the right are shown in figure 2. The friction, normal force, and gravitational forces exerted on the system center of mass, F friction, F normal, F gravity, respectively. The arrows represent only the direction of the force and begin at the point at which the force is exerted on the system. So there you go. Okay, let's see what we're going to do with this. Part A. An observer of the rider of the unicorn correctly makes the following claim. I always want you to back up claims. For the rider to maintain their balance, the rider's center of mass must be located to the right of the point at which the wheel is in contact with the ground. So let's go over here. Using appropriate physical principles, justify this claim, include qualitative reasoning beyond referencing equations in your answer. So we want there to be some sort of, for the maintain their balance. So maintaining their balance means we have balanced torques. That's just a common thing. If that didn't occur to you right away, that's just something that in your brain you should try to remember. If they're saying something's balanced, they're almost 100% of the time going to be talking about some sort of balance of torques. And balance of torques is great. It's, in some ways, it's better than unbalanced torques because then at least we don't have to deal with an acceleration. So there you go. I mean, at least an angular acceleration. So how do we do this? Well, I'm going to redraw these forces on here. So we had, just going from this diagram back here. So we had a friction force right here, and we had a normal force right there, and then we have this force of gravity right there. So I want to remind you that when you're dealing with torques, you can pick any point anywhere as your reference point for which you're finding the torques about that point, right? So I could pick a point over here, I could pick a point over here, wherever I wanted to pick that point. It's often nice to pick the center of mass of the system as your point for which you're finding the torques around. Or if you've got a situation where something's pivoting around a point, maybe you're choosing that point as it. So if you've got a rod or something and it's pivoting around this point, choose that as your point where you're finding your torques relative to. So in this problem, I think it makes sense to use this point that we're finding the torques relative to, and then we're figuring out how many torques are going in this direction and how many torques are going in that direction. And really, more or less what we're saying is that the torques have to balance each other out. So justify this claim. So I would start by something like torques need to be balanced. Torques need to be balanced. Okay, and that's not it. So we need there to be the friction force torque and the normal force torque. So I might call something like torque from friction has to be equal to torque from the normal force, or something like that. And then the idea is that this person has to be leaning forward. So if the center of mass were here, then my normal force torque wouldn't have any torque, right? Because it would be going through this point right here. And then I'd have my gravity, center of gravity would be this way, and my friction force would be causing some sort of torque, and the whole thing would start to rotate in this direction. So I would say something like the center of mass needs to be in front of the normal force in order for the normal force to have some sort of torque or something like this. So I don't know, COM needs to be to the right so that torque F is not 0. Something like that, right? So once again, if the center of mass were here, this torque, sorry, not torque F, torque N is not 0. So that the torque that's due to the normal force does something to actually rotate the system. So I think that that's probably would be good enough for that. Let's see for part B. For a given rightward acceleration of magnitude A, the rider unicorn, oh no, that's a different problem. The unicycle's center of mass is located at a constant distance h. Okay, h above the ground and d to the right of the point at which the wheel is in contact with the ground. So, okay, as shown in figure 3. Oh, I guess this figure 3 was supposed to be for this part B. So all this work could have been done on this figure back here, but that's fine. So derive an expression for A in terms of h, d, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so we know how to do this. So we're looking for A in terms of h, d, and g, basically. So let's do that one over here. So we're looking for the acceleration. So really, they're going to want us to start off with, since we're dealing with a linear acceleration and we're dealing with torques, we're going to want to make statements like F net equals ma and torque net equals I alpha, or something like that. And then for this one, we know that this is actually going to equal 0 because we have no, it's balanced. We're not rotating one way or the other way. So for this F net equals ma, remember we can draw a free body diagram. And even though the forces are scattered around, when we're dealing with forces instead of torques, we can still just draw a free body diagram like this. And I can draw FF, I can draw FN, and I can draw FG like that. Condense it all into one point, right? Just like that. For the torques, we have to worry about where they're acting. For the forces, we don't have to worry about where they're acting. So from here, if I was really going to break it down, I might say something like, in the y direction, I want my gravity to equal my normal force. And in my x direction, I want my friction force to equal ma. Oops, sorry, that went off the screen a little bit. So once again, gravity is going to be the normal force and the friction force is going to equal ma. So there's our a, and then we just have to put in a friction force over here. So you might be tempted to do, friction force is mu times the normal force, but that's going to get you into trouble a little bit because mu is not something that they want us to do here. That's where I went first, and then I realized that what they really want you to do is come back here to the net torque kind of thing. So the net torque thing, we want to have the friction torque, which is going that way, and the normal force torque, which is going that way. We want those two things to equal each other. So that means we can come down over here and I can say the torque due to friction is going to equal the torque due to the normal force, just like that. And now for these torques, we're going to start to figure out what the value of the torque is. So for this friction force torque, here's my friction force, and then, I got to get this other diagram. Okay, because that has h in here. So there's my friction force. Oh, sorry, it's going to be d for this one, and there's my distance d. Let's actually just draw them in back over here because that's nice to do. So that was h, and then this distance is d over there. So now we have it on the same page. So for my torque over here, for my friction torque is going to be, it is with the h over here, sorry about that. So it's this force, and then there's my moment arm. So if I draw it out here a little bit, there's my friction force, and then there is the distance from my friction force down, perpendicular distance from the center where I'm having my rotation point down to where my friction force would go. So the friction torque over here is going to be friction force times h. And then same with the normal force torque. The normal force torque is going to be the normal force times d, this distance over here. So d like that. So now from over here, I can write that equals that. So I can write my friction force times h is equal to my normal force times d. And then I can get, let's see, I have, how are we going to put this together? This one over here, I know that my friction force is ma, so let's do it that way. So let's put ma into there. So now I've got ma times h equals Fn times d. I also know that my normal force and gravity are equal to each other. So I know that mg equals Fn. So I'm going to stick mg in there. Yeah, there we go. ma times h equals mg times d. And now I can just say that a equals, the m's are going to go away. A is going to be g d over h. And I like when derivations work out to be something reasonable. And that's reasonable. I mean, who knows? You can get some very unreasonable derivations. but that one turned out to be reasonable. Okay, let's go back over here now. So that was this one. So part C says, consider the case where a small child rides on the unicycle. Small child. In this case, at a given rightward acceleration, okay, where the child maintains balance, the child unicycle system center mass is a constant distance, so it's half the distance above the ground and half the distance to the right that the adult was on there. Indicate if a child is greater than, less than, or equal to a by writing one of the following. Boom. So this is one of those unfortunate situations where if you didn't get this answer for part C, you're not going to get this answer for this answer for part B, you're not going to get this answer for part C. Although the AP people are going to say if you, in part C, if you reference this equation that you got, even if it's the wrong equation, as long as you're consistent with your equation, then they're going to give you the points for it. So whatever you got for part B, you need for part C. What that means is if you totally flub part B and you didn't get it, you just got to make something up. So let's say you completely flub part B and you don't know. Just write ... and then say guess, and you're going to write A equals, I don't know, you're going to write GH over D squared or something like that. You're going to put something in, you're just going to have to make something up because you need this formula for this problem. Now, I happen to have the right formula for this, so I'm going to do it in this section, and it's going to be right according to what the answer should be. But if you use this formula for this part and you use it consistently, they'll give you the point for it. That's my understanding. Hopefully that's the right way that it works out. So not using this one, so using this one, what's going to happen is if I take half of D and I take half of H, those halves are going to, oops, there we go. If I take half of D and I take half of H, those halves are going to cancel each other out. So I'm going to choose that a child is equal to the original acceleration and indicate, okay, good, so that's that. And then I'm assuming this next part here, which is on this last page, the next part says justify your answer. So now it says using the expression derived in part B, justify your answer. So here's my expression from part B. I'll say it again. I'll just write it down. A equals, what was it again? G times D over H. And I would write something like a child equals G times half D over half H equals GD over H equals A. And that would be my justification. So that's that. So interesting question, and I think that other than this derivation, I think that it was pretty straightforward. There you go.